Hi everyone, I'm Matteo Francia and today I'm presenting assess queries for interactive analysis of data cubes, which is a work I did with Matteo Golforelli, Patrick Marcel, Stefano Rizzi, and Panos Vassiliadis. The goal behind our work is that we want to compare business phenomena over multidimensional cubes. In this direction, OLAP provides some low-level operator to query the cubes, but our idea is that we want to provide higher abstraction that actually matches the analytic intention from the user. In this direction, some operators have been provided to complement the original OLAP operator, but none of them works in the direction of assessing business phenomena over cubes. So in this paper, we introduced the assess operator with the goal to compare some actual to expected behavior, as well as to judge the outcome of such comparison. If we want to do so in classical OLAP, well, then we need to query the cube, get a plain table as a result, and then to perform the comparison manually. This is hard if some transformation are needed, and even harder when more than one cube is involved in the comparison. So our contribution actually collocates within the intentional analytics model, which is the model that brings OLAP to a higher abstraction level, where the idea is that we want to express intention and not queries. So to each intention, we couple high-level syntax as well as the semantics to transform the syntax into an execution plan, for which we provide some logical and physical optimization. So for the assessment, the syntax is with cube for predicate by some level, assess a measure against a benchmark using a concatenation of function to transform the comparison, and finally, a labeling scheme. So the assessment actually involves many steps. So given a cube C that we call a target cube and a measure M, at first we need to specify a benchmark cube B that has a measure M prime that represents the expected behavior of M. Also, the cube B must be joinable with C, meaning that they should be defined on the same level. Then optionally, we can apply some transformation. So for instance, normalize the value. And in the end, we are going to compare the values of M and prime setwise and label the result of the comparison, meaning that we want to map the such value to a schema of predefined labels. We provide 4 benchmark types, so fixed, where we want to compare the cube against a fixed value, sibling, where we want to compare 2 slices from the same cube, past, where we want to compare a slice from a cube with respect to some value that we learn from an historic trend within the same cube, and finally the external benchmark in order to compare 2 cubes. We do not have time to go through all the benchmarks, so from now on, I will only focus on the sibling benchmark. So imagine that we want to compare siblings in our target cube with the purpose to assess if Italian sales are higher than French sales. So given our cube of sales, as you can see in the bottom right, an example of intention is with sales for country Italy by product and country, assess quantity against country France using, at first, we want to compute the difference between the Italian quantity and French quantity, and then we want to normalize the result with respect to the sum of total sales. Finally, the labeling scheme says, for instance, that we consider good the result if it's higher than 0.2. To implement the assess operator, we have 5 logical operators. The first one is get. So given a cube C, a predicate P, and a group by set G, we return a new cube C prime. Then we have the cell transformation, where given the cube C, we return a new cube C prime with an additional measure, and H transform is the holistic transformation, so is similar to the cell transformation, but when we want to compute the measure, we can draw values from all the cells on the cube. Then we have the join and the pivot operator. So basically, join put together the cube and the benchmark. So it's like a drill across. So given the cube of Italian sales, in red and the cube of French sales by product in blue. If we join the two cubes by product, then the result C prime represents the Italian sales, where in each coordinate you can find also the quantity from the corresponding cell in the French cube. So for lemon Italy, we find both the original quantity plus the quantity from the French cube. Pivot does something similar, but when we are working on a single cube. So if the two slices are now within the same cube, so the cube of sales has two slices, Italy and France, pivoting the cube by product and for country equals Italy returns a new cube C prime that again represents the Italian sales, and where in each coordinate you will find also the measure, the corresponding measure from the French slice. So notice that when we are working on a single cube, the join and pivot operator actually return the same cube. As I mentioned before, given our syntax, then we have a semantics that is translate the syntax into an execution plan. So to compute our assessment, given the cube of sales, at first we get the target cube, C, so the red one, we get the benchmark, so the blue slice, then we can partially join them on product and apply transformation and labeling. So for instance, first we compute the difference between Italian and French sales, that is 20, then we normalize them with respect to the number of sales. So suppose that the result is 0.2. So if the result is 0.2, our label in the end will be okay. Can we do better? So what we have seen so far is what we call the naive plan, where basically we get the target cube, we get the benchmark into SQL, and then we compute all the remaining steps into main memory. So can we do better? The idea is yes, if we push more operator into SQL to exploit the optimization strategy and structures that lives within the DBMS. So the fourth transformation moves from the naive plan to the join optimized plan, where basically we want to compute the join directly into SQL. And we can do that only if no holistic transformation is actually applied before the join. Can we do better than the join optimized plan? The answer is again, yes. And as we've seen before, if we are assessing a single cube, then we can also transform the join operator into the pivot operator. So in the end, our plan will be faster since we reduce the number of joins that are involved in our execution plan. So the empirical evaluation we carried out consider all the four benchmarks we have seen before with respect to cubes with increasing cardinality. So from 6 million to 600 million tuples. Noticeably, as you can see here, all the plans scale linearly. And as expected, the naive plan is always the slowest one. The join optimized plan performed better than the naive one, but worse than the pivot optimized plan. Again, not always the join optimized and pivot optimized plans can be applied. As expected, then, as you can see in the right chart, the past is also the heaviest benchmark since we need to apply some machine learning technique in order to learn the historic trend. In the end, in this paper, we have introduced the assess operator in order to evaluate a cube against a benchmark and then label the result. For such assessment, we also provide different alternatives for benchmark, comparison, and labeling schema, and also alternative execution plan to increase performance by pushing more operator into SQL. As a future work, we want to devise strategy in order to complete partial assessment. So for instance, if users do not specify the specific cube for a benchmark, we want to provide him or her the most interesting benchmark to compare with. Also, we want to increase the expressiveness of the assess operator. So for instance, allows user to apply transformation based on cell values. For instance, normalize with respect to the French population or Italian population, as well as we want to explore our logical operator in order to devise a cost-based optimization strategy. So thank you, and let me know if you have any questions.